All right. So I was asked by our training coordinator, Jim Bolisak, to do a demonstration on the NanoVNA and the TinySA. Still have a program booting on the computer for the NanoVNA, so we'll do the TinySA first. Now, SA stands for Spectrum Analyzer. Until recently, the Spectrum Analyzer was an extremely expensive piece of equipment, say 3 orders of magnitude more in cost than this device, which costs about $60 in the $50 to $70 range, say. And it's scanning, I think, 100 kilohertz to 300 megahertz here. It's got 4 different operational modes. Hello. There we go. It has a low input and a high input mode. That's for the spectrum analyzer. The low input is not talking about signal level, it's talking about frequency range. So the low frequency range is 100 kilohertz to 300 megahertz, and the high frequency range is 230 megahertz to 960 megahertz. Okay, so there's some overlap in the 2 ranges. And then it's got some low and high output ranges, which are, this is also a signal generator. So you can use this to align your radio or check sensitivity of your radio. So for the signal generator, we'll switch to low out here. And now it's in signal generator mode. You can set the frequency, you can set the output level, you can set the modulation, and you have a choice between none. 2 AM modes, one with a 1 kilohertz modulating frequency and one with a 10 hertz modulating frequency. Then it also can do narrow band FM and wide band FM. I think it uses a 1 kilohertz audio tone for those. So, you can either receive off an antenna and transmit off the antenna or connect it directly to your radio. We'll go back to, well, let's see, let's demonstrate the signal generator. Set it for 50.55 megahertz, AM modulation at a 1 kilohertz tone. Turn it on, and I can have a radio here that'll receive that. Set to 50.55 megahertz. So, so as long as I got the radio on, we'll go back to signal generator mode, or spectrum analyzer mode, rather. We were on signal generator mode. And I'll transmit at 50.5 kilohertz AM.
Okay.
So we're putting out a carrier. You can see that peak down toward the lower end of the spectrum is our signal that we're transmitting. I'll stop transmitting now. And the signal goes away. These are like wireless modem signal.
Okay, everybody, somebody bought a box of tubes from John over at the table right here and then left them there. So if you're in here, you better come and get them, because I told John you might as well take them home. So you get 5 minutes to go pick them up, and otherwise they're going home. Thank you.
Okay, and we can change the range on this. You can choose where you stop and start the frequency scan, or you can put in a center frequency and the span range. So All that stuff is variable. You can operate this from the screen like I just did, or there's software. There's a USB port. You can hook it up to your computer and run it through software.
So you basically give you an application put on your laptop or whatnot as well as part of it, right?
Well, no, it's not provided by the people that make this. These are just people who have written the software to, it's just a regular, like a serial port. On your computer, it shows up as a COM port.
I see.
So it's very, very low level protocol stuff I don't know anything about. But anyway, it's just people who have written the software as a labor of love,
Yeah.
and make it available. It's all freeware.
Yep.
So now we're going to the NanoVNA. Let's see if we can get this to work here. So NEVNA, which is Vector Network Analyzer, this one is a 2-port device. So basically it has an input and an output. And you can extract all kinds of parameters, but basically it's measuring two things. In the first port, channel 0, it measures the S parameter S11 in the S matrix, which is reflection loss. And in the second port, which is referred to as channel 1, measures S21, or insertion loss. So what we have hooked up to it here is a filter, a Collins filter with a 455 kilohertz center frequency. I'm not sure what the bandwidth is, but we can look at it. And I am going to run it. I could run it from the screen, but I'm going to run it from the computer here. So I'm going to start, actually I'm going to load the calibration first. I'm going to use a real mouse here.
It works. Fully tested. Yep. Everything's been tested.
So I've saved the calibration.
These over here. These are the weak games. Oh, yeah, that one does weak and weak.
Load it. And now it says we have the calibration loaded.
Okay.
Get rid of that screen. And I'm going to set up the sweep range. I'm going to go from, it's a 455 kilohertz center frequency, so I'll go like 435 kilohertz to, let's say, 475 kilohertz. And I'll have 30.6 hertz per step, which is enough resolution. I can change that if I wanted to, but I'll just sweep it, see what we get.
So let me know if I'm in your way.
Nope, you're not in my way. Why aren't we sweeping? Oh, not connected. I forgot to connect to NanoVNA. I thought I'd already done this, sorry. Get rid of that. Okay, now we're connected. Now we can sweep it. Actually, it goes through its own sweep first.
Okay. Yeah, one of the goals here, this is a test run as well to see how well this does, and also, I'm not sure how well it'll pick up the screen, but we'll find out.
Yep, we'll find out. It's actually going to show up on two places. It's going to show up on this screen, and it's going to show up on this
Oh,
one.
that's nice. And you're saying that's the freeware that you loaded on there.
Yep. Yep. So
It's a pretty nice looking freeware, looks like somebody put a fair amount of energy into that.
yeah,
So
yep.
nicely done.
Yeah, this particular program is called NanoVNA Saber, and I'm running version 0.2.2-1. I don't know if that's the most up to date or not, but it uses Python, and this particular version, somebody's packaged it into a nice .exe file that you can install easily into Windows 7 anyway, so that's what I did.
I see.
I've actually got Windows 7 running in a virtual machine inside a Mac.
Oh, okay. I was going to say, I was wondering whether it would be back compatible.
It is actually, since it's written in Python.
Yeah,
I can run it native in the Mac as well, but the other program for the TinySA, I have to run in Windows 7, so I just decided to do them both that way. So anyway, what we see here is the response of the filter come in this graph here, and also in the violet graph on here. I don't know if you'll be able to see it on the video, but there's a violet graph with the same filter pass band showing up.
I haven't zoomed in. We'll find out. This is a great understanding for me to understand how well this does and what I can and can't do with it.
Sure. And this is of less interest to us, but this is the reflected energy coming back into the first port here as a function of frequency. Okay. So this is showing basically loss versus frequency as we scan between 535 kilohertz and 435 kilohertz and 475 kilohertz. So you can see down here we're at minus 80 dB. We've got noise, very low gain, pretty much the noise floor of the instrument. And then we start to see the signal coming up. And then we have our filter pass band here. The signal starts coming back down, and then we're back into the noise. And we can turn on some markers here and do some measurements. So I turned on my first marker. I can click on the graph, bring it over here. So the center frequency it's saying is 455.007 kilohertz approximately. I didn't put my marker exactly on the center, maybe. I was trying to, but as luck would have it, we got 455.007. And then if we want to measure the pass band, it's at the top of the pass band, it's measuring an insertion loss, and that includes the insertion loss of the filter plus the setup of minus 15.9 dB, which is high, but I didn't do a real precise, accurate calibration before I started this, because I'm just trying to demonstrate the capability.
Right.
I'm not trying to get quantitative information
Right,
here.
sure.
But let's say we wanted to measure the pass band. We can go, say, 20 dB down from that. We'll turn on another marker. And we're at minus 15.8, so if we go to minus 35.8, approximately, well, minus 36.8 looks like it's about as close as we can get. And then on the other side of the response, we can turn on our third marker. And let's see. Okay, so minus 37 dB. All right. So the difference between these two frequencies, 458.9, let's call it 459, and 451.7, let's call it 452. So at the 20 dB points down, we have a pass band of 7 kilohertz, which is, kind of narrow for amplitude modulation. You know, you'll start to cut off some high frequency response, but in a crowded band, it might be something you'd want to use. Get rid of the adjacent channel interference.
Sure.
So let's see, one more demonstration I can do here is I can scan the SWR. You can pause it if you want, John.
All right.
Okay, I'm not sure where I left off, but I guess we were looking at a filter with the Nano VNA. Another thing we can do is do a single port measurement on a single port network like an antenna. All right? And that's very useful to hams because when you're transmitting, it's usually important that your antenna is resonant on the frequency you're transmitting on. And there's a bunch of ways to make that happen, but that's beyond the scope here. But what we can do is we can get a graph of standing wave ratio, which is a measure of how good a match we have to 50 ohms, which is usually what we're after, over a range of frequencies. Now, this came off of this radio, which actually can transmit on 4 different frequencies. The 50 megahertz band, the 144 megahertz band, the 220 megahertz band, and the 440 megahertz band. So it's a VHF, UHF transceiver. And this is the antenna they sell with it. So ideally, this antenna would have a resonance somewhere in the 50 megahertz band, somewhere in the 144 megahertz band, somewhere in the 220 megahertz band, and somewhere in the 444 megahertz band. I don't know that it does. As a matter of fact, I've looked at it before, and I know that it doesn't. But it still kind of works, but it's not optimum. But let's look at it anyways, for the purposes of the demonstration. So I'm sweeping from 40 megahertz to 500 megahertz to cover that range that we would hope that there's resonances in. And I did something wrong. Data outside. Oh, I think we're getting it.
It's a limited
I don't know why the VSWR curve isn't. Okay, we don't have really high resolution here.
Yeah, it'll be hard to see. Well, who knows?
No, I mean, on the sweep, I should have done more data points. Let me see if I can do a little better than that. It'll take longer for the sweep, that's all. So you can see down here we're starting to get our return loss curve.
Oh, yep.
And SWR is just a transformation on the return loss curve, which is the S11 parameter. So we are seeing some resonances. They're not necessarily where we want them. We'll measure them. So a high negative return loss you'd think would be a bad thing, but it's a good thing. That means it's a good match, so it's a low SWR. And so these negative peaks should be in roughly the same position on both graphs. And we're done with the sweep. Okay, so I'll turn on our first marker here and find out where the first peak is. So you got so there's a slight resonance at 43 megahertz, which is the closest one to 50 megahertz, and the SWR is still 12. Typically, you'd want to see less than 2, 2.5 to 1, so it's really high.
Okay.
We can go on to our next resonance here, which is a little better. Okay. So it actually looks like it gets a little lower. I wonder if the arrow keys work. Okay, good. Okay, so looks like we have a resonance at 107 megahertz right in the FM broadcast band, at the top of the band.
Yep.
And the SWR is a reasonable 1.3. That's on this graph up here. Look to be some other resonances. Let's see. We have one at 120 megahertz about. One at about 130, and then one at 233, so presumably that's supposed to be the 220 megahertz band. It's a little high. And nothing up on the 444 megahertz band to speak of, so.
No, that's my house.
Anyway, this is the antenna they sell with the radio. They probably could have done better, but that's what we got. But this is useful, like in the HF spectrum, when you're stringing out the wire and you're printing the antenna to frequency. You can use an instrument like this to. And like I don't know if there is a resonance up there. I guess it's missing. Of course, you can make this change the readings by touching it and putting it toward, near metal. So that could be influencing our results a little bit, but for this purposes of demonstration.
No, that's terrific. I mean, it gives a sense of what the capabilities are, and more so to beg more questions probably from you, especially since you're probably becoming more and more of an expert as you use it more.
Yeah, I mean, I've just scratched the surface. I mean, this is such a capable instrument. There's all kinds of things you can do with it. You can measure the length of coax. If you know the velocity factor of the coax, you can just have a open or shorted, like the coax with an open or short at the end, and do what they call a time domain reflectometry measurement. But it's and calculate the length, or with the known length, calculate the velocity factor. And I haven't even played with that yet. And there's all kinds of network measurements you can make that I've never even tried. I've just looked at filters and used it as an antenna measurement tool. And like the TinySA, you can control it from the screen and use it as a standalone instrument.
Oh, that's terrific.
Yep.
So Larry, thank you very much for that. You know, it's a nice taste for us. We'll probably beg for you to do a demo on a Zoom meeting when you feel ready, when you've mastered more and you want to do some demos with radios and so forth, and people might, I'm sure, will ask you a lot more questions.
Yeah. Okay. Yeah, we can do that. We can maybe hook a signal into a radio with this.
Yeah, that'd be perfect. Thanks, Larry.
All right. Sure.